Okay, guys. So this task was supposed to help bring back memories of last year when we did transformations. Hopefully, show some of you for the first time what transformations are if you're new to our school. So if we take a look at this summarizes everything we learned last year about transformations. We studied 3 different transformations: translations, the shifting, reflections, and scale changes. So for us, the scale changes were our stretches and compressions. So to shift, the first one talks about adding something or subtracting some number from your x. So when you add or subtract to your x, that's obviously going to affect your graph in a horizontal way. So this gives us the horizontal shift. Now, when it affects the x, it always affects it in the opposite way. So if we add something to the x, it's actually going to send it left that many units. Or if we subtract something from the x, it sends it right that many units. So that's the transformation that takes place when we add or subtract something in our function to the x. Now, if we take and just add or subtract something to the end of the function, that's going to shift vertically. So if we add it, it shifts it up in units, and if we subtract, it shifts it down in units. So when it's not affecting the x, we do exactly what it looks like. When it affects the x, we pretty much do the opposite. And we'll prove when we get to the back of this page, that is true. Now the reflections, if we negate the entire function, can't we think of f of x as y? That's where we change our y's to the opposite. And when we change our y's to the opposite, what does that cause it to do? Reflect over the x-axis. Versus when we change our x's to the opposite, that causes it to reflect over the y-axis. So that's a reflection over the y. Okay. Now, the 2 types of scale changes you studied last year were vertical stretches and compressions and horizontal stretches and compressions. You may have used the word shrink instead of compression, which is totally fine. I tend to use the word compression because when I think shrink, I think get smaller in every direction. And for us, when we talk about a vertical compression, we're talking about you can think of it as being squished vertically. Like if I were pushing down vertically, it squishes it out. It doesn't make it smaller. When I think shrink, I think of the shrinky dinks we used to color and put in the oven, and they would shrink and get smaller. Did y'all ever do those? No? I feel like we should have like a special Saturday where we all meet and do shrinky dinks if you haven't had a chance. Oh, those are so much fun. But in terms of vertical stretches and compressions, when we think shrink, it's really only with respect to one direction. It's not shrink in every direction. It's shrink vertically or shrink horizontally, not both. And so that's why I use the word compression, because that makes me think I'm squishing something. I'm pressing it down. And when I compress a parabola, it kind of squishes it from the top. And it makes it open up nice and wide. Yes, ma'am?
So would a vertical stretch be the same as a horizontal compression?
Sometimes they are the same, like with certain functions. For example, an absolute value function, the vertical stretch and horizontal compression can have the same exact effect. Now with others it does not. We can usually, with our functions, write a horizontal compression as a vertical stretch, but it may not even be the same numbers. So anyway, if I were to give you a graph and ask you to give me the function, of course I'd have to take both answers. You gave me a vertical stretch that works for that graph, or horizontal compression that gives me the equivalent, I would take both. And sometimes they are the same and sometimes they're different. So a vertical stretch is if this multiplier is greater than 1. And the reason I have absolute value is because we kind of ignore the negative here. Because what does the negative do? It causes a reflection. So I'm really ignoring the negative. That's why I have the absolute value there. Yes, sir.
Are you supposed to be recording?
I am.
I was like, you said that before we started.
I think I am. Did y'all see me start the record?
I saw you when
Okay. All right. And then compression would be where it's between 0 and 1. Now the horizontal stretch is where it's between 0 and 1. So once again, we have to think differently. So if we have like a multiplier here of 1/2, that's actually, when it affects the x, we have to think opposite. What is the opposite of multiplying by 1/2?
2.
Multiplying by 2. So that, if the multiplier is between 0 and 1, that's actually causing the stretch. And if it's greater than 1, it's a compression. All right, so let's take a look. There's the blank page. Here's the filled-in page at the graphs here. So what does this do? Well, this -4 just is going to take the whole function and shift it down 4 units. So we take our parent graph, look at these ordered pairs, and drop every single one of them down. Subtract 4 from the y for every one of them, and it lowers our function. Okay? This one is x -3. So it's going to shift it right 3. So we take all these ordered pairs and move them right 3, or add 3 to our x value. Here we have the negative inside with the x. The negative inside with the x changes all the x's to the opposite, which causes our function to reflect over the y-axis. So it should be like a mirror image over this y-axis. Now this one may be the one that you weren't sure what to do with. This one had the function f of 1/2 x. So the 1/2 is inside being multiplied by the x. So we always do the opposite. So what's the opposite of multiplying by 1/2? Multiplying by 2. So we would take all our x coordinates here and multiply each one of them by 2. Now, does it look like, when you compare the original function here with the transformation, the transformed function here, does it look like it's been stretched horizontally? Does it look like it's been pulled out horizontally? Because that's a horizontal stretch. Do you see how it looks like it's just been pulled? Okay. This next one, took each point, moved it left 2. F, moved each point right 1 and down 2. Now this one did a couple of things. With our y's, they're going to all change to the opposite because it's the negative f of x. So that's a reflection over the x-axis, which changes all the y's to the opposite. So we flip it and then move up 3. And then this one, we would double all our y's because it's 2 times the function. And we would shift it left 3. Yes, Sid?
I have a few questions. If it has like a +3, do you shift it first or do you subtract it first? Or does it matter? No.
We would kind of follow order of operations.
Okay.
So like on this one, we would flip and then
Okay.
we do that multiplication before we do the addition.
Alright.
I see what you're saying.
And
on this one, we could work inside our parentheses and then do the multiplication.
Alright, and the second question is what would number would letter H be called? Would be called a vertical stretch or vertical?
That is a vertical stretch by a factor of 2.
Okay.
Yep. With the vertical ones, what it looks like is what it is. So if this is a 2, it's a stretch. If it's a 1/2, it's a compression. With the horizontal ones, you always have to think opposite. So it's 1/2, so in our brain we're going, 1/2, that seems smaller, but I'm thinking opposite. So it's going to be a horizontal stretch, and it even looks like it's been pulled. Okay, and then let's look at these. Now these were just shifts. I didn't give you any stretches or compressions, or I didn't even give you a reflection, did I? No. how did you guys do on this part 3?
I mean, definitely.
Yeah, I do that here.
Okay, those of you that
I'll make
got
sure
there,
some-
were you okay?
Yeah.
Okay.
Pretty much just
I put some subtract.
No, this other one did it. Okay.
Everyone.
Oh. Okay, let me go ahead and get rid of this too. There we go. Alright, so last year you were basically given the picture
Yes.
of a parabola and you moved it around. This year we're actually studying this quadratic function. And the parent graph for our quadratic function is this. F of x equals x squared. And so all we're going to do once we master this function is we're just going to move it around. You see how we're moving it, transforming it, moving it around? So, I gave you a table here, but you probably didn't even need it. Because a quadratic function is a squaring function, isn't it? F of x equals x squared. What do I do to my input to get my output? I square it. It's a squaring function. I don't think that has 2 R's. There we go. Alright, so if I move left or right 3, what is positive or negative 3 squared? 9. If I move left or right 2, what is positive 2 or negative 2 squared? 4. If I move left or right 1, what is positive or negative 1 squared? 1. So here it is in the long form, and here's what we're just thinking in our head, because we don't need to write that table. We can square numbers very easily.
Yeah.
So, this is what we do if we just randomly pick things and input them into our function. Not really randomly, but the values of x from negative 3 to positive 3. Negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And it gives us our parent graph for the quadratic. And just like we found, if I started with my vertex here at 0, 0, if I move right or left 3, I would go up 9. If I move from this vertex out 3 units, I would go up 9, because positive 3 or negative 3 squared is 9. If I went right or left 2 units, 2 squared is 4. 2 squared is 4. If I went right or left 1 unit, I'd go up 1 unit. 1 squared is 1. Negative 1 squared is 1. And that's how we form the parent graph. So now I want us to think of this problem as in shifting, transforming our parent graph. What would this function, how would it change our parent graph? What would it do to it? Right 2 units. So we start off going over right 2 units, and since the vertex of this graph was at 0, 0, when I go right 2 units, that's my vertex, isn't it? Now, from the vertex, I want you to think about this in terms of moves from the vertex. And these moves are because this is a squaring function. If I went right 1, what's 1 squared? 1. Left 1, what's negative 1 squared? 1. Right 2, what's 2 squared? 4. Left 2, what's negative 2 squared? 4. And then I have my function. And all I did was shift the parent graph. Now, could we graph this by testing points? Sure. Let's say you were just picking some points to see how it looks. If I plug in negative 3, ooh, I get out 25. If I plug in negative 2, I get out 16. If I plug in negative 1, I get out 9. If I plug in 0, I get out 4. If I plug in 1, I get out 1. If I plug in 2, I get out 0. If I plug in 3, I get out 1. Well, it took me a while to even find numbers that would work for me, didn't it? Could I make a table and graph it? Sure. Was it quicker just to shift the vertex? Yes. And that is why we like to graph given transformations. It's quicker. It's nice. It's simple. All right, so here we have x squared plus 3. So what does that do to our parent graph?
Oh, it's up 3.
Up 3. 1, 2, 3. There's my vertex. So because this is a quadratic, my parent function is a squaring function. The moves from the vertex just get squared. So if I went right 1, 1 squared is 1. Right 2, 2 squared is 4. Left 1, negative 1 squared is 1. Left 2, negative 2 squared is 4. Done. Does that make sense? All right, where would the vertex shift for letter C?
Left 2, down 1.
Left 2, down 1. My vertex is located at the point negative 2, negative 1. And I do the same moves. When will I not do the same moves? When will those moves change?
Hopefully
Shrink or
dilation.
compress.
Very good. If there's any type of stretch or compression, and they may change when there's a reflection. Okay. So this one, where's the vertex on D?
Negative 4x.
Negative 4, 0. Okay, this one does have a negative out in front. The negative is out in front of the entire function. It is not in parentheses with the x. It's out in front. A negative out in front causes what type of reflection? Over the x-axis. So it switches all my y's to the opposite. So instead of going over and up, we'll go over and down. Matt Hill, I saw that. Whoops, I skipped. Sorry.
That's not good, man.
All right. What do you think about this? It's all right? Okay.
I like this.
All right. So tell me about the shifting. What kind of shifting? Where can I find my vertex? Up 2. 0, 2. Okay, the negative lets me know my parabola is going to open which way? Up or down?
Down.
Down. Okay. Now what would the 1/2 do?
It, vertical shrink.
It is. So instead of going left and right 1 and down 1, we're going to go down a half. Instead of left and right 2 and down 4, we're going to multiply that by half, which is the same as dividing by 2, right? So we're going to go down 2. Instead of left or right 3 and down 9, we're going to go down 4.5. Down a half, down 2, down 4.5, down a half, down 2, down 4.5. So it's hard to tell in mine because I'm not the best at drawing these on the maybe, but it did make it wider than the other. A vertical compression widens out your quadratic function. Okay, you try the big one. Does your graph look like mine?
Kind of.
Yeah.
Kind of. Okay, so our vertex was at 1, -8, and my moves were doubled. So instead of 1, 1, I go over 1 up 2. Instead of 2, 4, I go over 2 up 8. Instead of 3, 9, I go over 3 up 18. And that happens in both directions. And the reason they were doubled was because of the 2. Okay, domain and range. These are the characteristics that I've asked you to add to 1 through 4 on your homework. These characteristics. Okay, so domain and range. Domain, x values. Does this parabola continue to widen forever left and forever right? It does. So how would we describe the domain? Yes.
Real numbers.
Negative infinity to positive infinity. You are correct. All real numbers is how we can say it in words.
Okay.
Symbolically, we can say negative infinity to positive infinity. We will usually use interval notation in here, but you are correct. All real numbers means the same thing. Okay, range.
-8 to positive.
Very good. It goes from -8 to positive infinity. Now, we cannot contain infinity. Infinity isn't a real number. We can't get there. It's an idea. But it does include the -8. So we should also include the -8. If this were on a standardized test for people in your grade, it would probably look like this. Y is greater than or equal to 8.
That's why.
Okay? But we will be using interval notation, and we are consistent in that at Stark Mill because you're on the track to take calculus. That's why we do it. Okay, x-intercepts. Well, we can read them clearly. They're at -1, 0 and at 3, 0. The y-intercept, we can also see clearly, is the point
0, -6.
0, -6. We will solve those algebraically soon also. Increasing, decreasing. Okay, so we always start on the left side, and as I go from left to right, what am I doing to start with? Decreasing. And when I taught this last year, what we did was we would draw the number line at the very beginning. We would draw the number lines for increasing, decreasing, and we'd say, okay, any max or min we list here, what's that y value? 1. From negative infinity to positive infinity. What did it do from negative infinity to 1? It decreased. What did it do from 1 to infinity? It increased. So we have an increasing interval from 1 to infinity and a decreasing interval from negative infinity to 1. Now, it's acceptable to use the parentheses or the bracket here. I always use parentheses because at this point for me, I don't consider it increasing or decreasing. But I've seen both used. You can use either. In behavior, as x approaches negative infinity, what is the function doing? The function approaches positive infinity. And as x approaches positive infinity, y also approaches positive infinity. And I'll use f of x or y there. Over what intervals is the function positive? Well, this is easy. It's positive right here, and it's positive right there, above the x-axis. So this is positive from negative infinity to -1, and then again from 3 to infinity. And we'll use the union symbol, meaning put them together. See if you can do the negative. Oh, sure. Okay. Okay, so this is negative from here to here. It is below the x-axis, therefore the value of the function is negative from -1 to 3. Does this have a max or a min? This is our minimum. And on a quadratic, the minimum always occurs at the vertex. And what is that point where it occurs? 1, -8, which is the vertex of this function. And if we were asked to give the axis of symmetry for this function is where I could draw in a vertical line. such that it was a mirror image of itself on either side. So that is that line. How do I describe a vertical line? X equals 1. Don't forget the x equals. Because otherwise you're not giving me the axis. You're not giving me the line. Let me stop the recording and I'll answer any other questions.